Good morning. So today we are going to learn about rate equations to second part of the rate equation in laser. I am Dr. Raghu A, working at Government College Autonomous Mandya. So this is the outline of today's talk, revision, three-level laser system, and we will make some conclusion about that. So first let us revise what we have studied in the earlier class. Basically, we took a two-level system and we examine whether lasing is possible or not. So, and if you write rate equations and you solve, you get this expression for rate of populations in the two levels, N2 to N1 as equal to W12 divided by W12 plus T21. Note that RHS of equation 1 contains numerator as a denominator. Denominator is more than 1, more than the numerator. Therefore, RHS is less than 1. This implies N2 by N1 is less than 1 or N2 will be less than 1, which is not a condition for population inversion. The condition for population inversion is that N2 should be more than N1. However, this ratio N2 by N1 can be increased if you increase the radiant intensity to a maximum value that is related to W12. Even with the increase of W12 to a higher value, at best N2 can approach only N0 by 2. Now this is still a condition which is less than the population inversion. Population inversion requires N2 to be more than N0 by 2, where N0 represents total population of the atoms in this two-level system. So combining all these, we can conclude that lasing is impossible in a two-level system. Now keep this information in your mind and let us proceed to next system, three-level system. So this diagram actually shows two energy levels N1 with populations N1 and N3, energy values E1 and E3. E2, N2 are respectively energy and populations of the second level. It is a metastable. A metastable state is one whose lifetime is more than the normal lifetime of any other higher excited states. Lifetime of normal excited states is of the order of 10 power minus 8 seconds, whereas metastable state will have lifetime more than that. It could be millisecond. Some of the metastables could be even having lifetime of few seconds. So this is general picture about three-level system. Now in this three-level system, total number of particles is conserved. If I call N0 as the total number of active atoms, then that is conserved. So if that is the case, then one can write N0 equals N1 plus N2 plus N3. In most of the time, number of atoms will be either in N1 or N2. Therefore, this expression can be approximated as N1 plus N2 only, because in actual measurement, number of atoms in the level E3 will be very, very small. So N0 is nearly can be written as N1 plus N2. Keep this relation also in your mind. Now three-level system has one extra metastable state compared to two-level system. Therefore, atoms which are in the level energy level E3 undergoes spontaneous decay to E2 through a radioactive non-radiative transition, radiation-less transition. Now because of that, rate of spontaneous decay from E2 to E1 is slower than rate of the spontaneous decay from E3 to E2. This is because E2 is a metastable state. So this gradually increases population in the level E2 and finally achieves population between E2 and E1. E1 corresponds to lowest level, normally called as ground state. E2 is first excited state, it is a metastable in this case, and E3 is the second excited state. So in this scenario, lasing transition can take place from E2 to E1. So this is actually the possible thing in a three-level system. So if WP denotes pumping radiation transition probability from E1 to E3 or E3 to E1, then number of atoms which are going to undergo excitation from energy level 1 to energy level 3 or energy level 3 to energy level 1 transition, it is a de-excitation, depends on induced by this radiation. WP is, although it is the transition probability, contains information about radiation density incidenting on the system. So if WP is that, then the two type of transition can be rewritten like this. WP makes a transition from energy level E1 to E3, and also WP induces a transition from E3 to E1. Note that we already learned that in a just two level system, no lasing action takes place. Therefore, even though the WP induces a transition from E3 to E1, there can't be any laser transition because population inversion cannot be achieved between E1 and E3. So in addition to that, there is one more transition which can take place from E3 to E1, which is spontaneous emission, and that transition from E3 to E1. A31, which is shown next to the transition, is actually a spontaneous transition probability. So also another transition is possible from E3 to E2. That transition is denoted here as S32, where S32 is actually non-radiative transition probability from E3 to E2. A31 corresponds to radiative transition probability, whereas S32 corresponds to non-radiative transition probability. Tau 32 is a lifetime of excited state E3 between the transition from E3 to E2. Now let us start writing rate equations in this particular system. Note that this has three levels, N1, N2, N3 are the populations of the corresponding three levels. So we can write rate equation for all these three levels. So let us write the rate equation for one of these levels. Let us begin with the third level, E3. So rate of change of population N3 of E3 basically depends on the gradient in density which is incidenting on the system, and also on the number of particles in N1 and in the energy level E1 and energy level E3 respectively. So pump transition to E3, which raises atom from level E1, and induced transition from E3 to E1 is given by this expression WP equals WP into N1 minus N3. WP N1 represents the phase pump transition, which depends on the radiant intensity, density, and number of atoms in the ground level N1. So it is this particular transition increases the number of atoms in the N3, therefore that's a positive sign. Whereas the de-excitation transition from N3 to N1, it depends on WP N3, decreases the population of N3, therefore it associated with a negative sign here. The second thing is any atom which goes to E3 level undergoes non-radiative transition to the level E2, and it decreases number of atoms in N3, therefore it is associated with a negative sign, and its value is given by minus S3 to N3. N3 is population of third level. S32 is transition probability, and it also depends on spontaneous transition to the E1, and 831 is a spontaneous transition probability. So using all this, one can write the rate equation of N3 as dN3 by dt is equal to sum of these three things, Wp N1 minus N3 minus S32 N3 minus A31 N3. Keep this equation 2 in your mind because we will be using this equation again. Now let us write rate equation for the level energy level E2 with a population density N2. So that depends on rate of change of that N2 depends on again three factor stimulated emission, which makes a transition from E2 to E1 and that produces laser light, and again induced absorption in a reverse direction. So combining that we can write that is proportional to minus W21 into N2 minus N1. Spontaneous transition from the level E3 to E2 actually increases number of particles in energy level E2, therefore it carries the positive sign S3 to N3 here. And spontaneous emission to the level E1 from E2. This transition decreases the number of particles in the level E2, therefore it is associated with negative sign. So with this actually one can write rate of change of population level in N2, which is the rate equation, and that is equal to dN2 by dt equals minus W21 times N2 minus N1 plus S32 N3 minus A21 N2. Also remember this equation 3, we will be using that equation also later. So this energy level diagram we already noted down. So in this diagram you are showing three transition from ground level to third level and vice versa, both radiation induced as well as spontaneous induced downward transition and non-radiative transition to from E3 to E2. So after when population inversion situation arises between E2 and E1, lasing transition can take place with the incident of external radiation whose frequency matches with the frequency of the emitted radiation from E2 to for the transition from E2 to E1. So in addition to that, there is also an upward transition which is again induced absorption between E1 and E2, that is not shown in diagram. And spontaneous emission from E2 to E1 is also possible. So that is shown here. A21 represents radiative transition probability from E2 to E1. And W21 in the diagram actually represents stimulated transition probability from E2 to E1. There is also another transition, simulated transition probability from E1 to E2 that is not shown in this diagram. So basically we have 6 transitions in 3 energy level system. And we shall write the rate equation for the remaining level N1 of E1, and that depends on pump transition of atoms from E1 to E3, which is given by minus omega p into N1 minus N2. Stimulated transition from E2 to E1 and E1 to E2 both, that gives rise to W12 times N2 minus N1. Spontaneous emission from E2 to E1, which is equal to A21 times N2. So that is that transition, third transition increases the number of atoms in the N1, therefore it carries with a negative sign. So with this one can write the rate equation for N1 as minus Wp times N1 minus N3 plus W21 times N2 minus N1 plus A21 N2. So that's the rate equation for N1. However, if you carefully observe, this can be also be written as a negative of rate of N2 plus N1. Therefore, this rate equation of N1 is not completely independent. So we can then concentrate only about equation 2 and equation 3, which are rate equations for energy level 3 and energy level 2 respectively. Under steady state condition, the rate equations reduces to 0. That means dN1 by dt equals dN by 2 by dt plus which is equal to dn3 by dt to 0. So this is the condition for steady state. Now this steady state condition can be applied to equation 2, also for equation 3. First let us apply it for 2. So when we substitute that in equation 2, we get this. So that right hand side becomes 0 for this equation. That equation can be simplified for Wpn1. So by sending the remaining terms to the right hand side. And finally this equation can be simplified to n3, and n3 will be equal to Wp times n1 divided by Wp plus S32 plus A21. That's the equation. Now in this equation you must note that E2 represents the metastable state and E3 represents a normal state. So that actually tells that there are more number of transitions from third level to second level than third level to one level, and that implies basically S32 will be much greater than A31. So with that, A31 in equation 5 can be neglected. Now if you neglect A31 in equation 5, then one can easily write the value of population of the third level as equal to Wp divided by Wp plus S32 times N1. So we use this equation 6 later also. Keep that equation in your mind. Now under steady state condition, equation 3 also reduces to 0, and that equation can be written in this manner. Now that equation further simplified like that, and this can be solved for n2, and before doing that we will substitute the value of n3 from equation 6, which was derived in the previous slide, in the above equation, and n3 is actually Wp divided by Wp plus S32 times n1. So if you take n1 common in the, it is after substituting, you get left hand side to be equal to W21 plus Wp times S32 divided by Wp plus S32, and right hand side is written as it is. Then rearranging the terms and estimating the value of n2 by n1, you get n2 by n1 equals W21 plus times Wp plus S32 plus Wp times S32 divided by having some denominator W21 plus A21 times Wp plus S32. This is equation 7. So to simplify further, since this is a 3-level system, what we will do some mathematical juggling here. We will add and subtract by 1 equation 7 independently. First let us subtract equation 7 by 1 on both sides of equation 7. We get this terms n2 by n1 minus 1, which is equal to right hand side of equation 7 minus 1. So you can simplify this right hand side and you can simplify left hand side separately. Left hand side becomes n2 minus n1 divided by n1, and right hand side becomes this expression. That's simply algebraic simplification. Now in the next we will add 1 to equation 7 on both sides. You get n2 plus n1 divided by n1, which is equal to this particular part. Since both these equations are derived from equation 7, the denominator of equation 8 and equation 9 are same, whereas numerator are different because in one case we are subtracting by 1, in another case we are adding by 1. Taking the ratios of equation 8 to equation 9, the denominator of the two equations are being common, they will get cancelled. Numerator of equation 8 divided by numerator of equation 9 will be the values here as shown in this expression. So n2 you get n2 minus n1 divided by n2 plus n1 equal to RHS of equation 10. So this is an important relation, note that in your mind. N2 minus n1 represent the population difference between the ground level and the metastable level E2. And N1 plus N2 is nearly equal to total number of atoms present in the system. So that can be simplified in this manner. N2 minus N1 divided by N2 plus 1 can be written as delta N by N0. Now keep this equation 10 in your mind, so that, and also especially numerator in your mind, that we are going to use it. So numerator contains Wp times S32 minus A31 minus A21 S32. The population inversion condition requires that the difference between N2 and N1 should be more than 1. Only if it is more than 0, then only we say that the system has achieved population inversion. So we can solve for the population inversion for that. Then rewriting that for the population inversion condition, we get this expression from the previous expression. So Wp should be greater than A21 divided by A21 multiplied by S32 divided by S32 minus A21. So A21 is, we can divide the entire equation by A21. If you divide the entire equation by A21 on the right hand side, you get the condition for population inversion, which is given by this expression 11. So the condition requires that radiation intensity, radiation induced transition probability to be greater than A21 divided by 1 minus A21 by S32. Correction, earlier I told you it should be divided by A21, instead it should be divided by S32. Anyhow, you can do that calculation, it's not difficult thing. Now all these A21, S32 are actually related inversely to the lifetimes of their excited states. Therefore, that equation 11 can be written in this manner: Wp is greater than 1 by tau 1 divided by 1 minus tau 32 by tau 21. So that can be further simplified and rearranged in this manner, in which actually everything is multiplied by tau 21. So the condition, population inversion condition, is better expressed in known quantities like lifetime instead of unknown quantities or indefinite quantities like transition probability A21 or S32. So this Wp must be greater than 1 by tau 21 minus tau 32 is the condition for population inversion in a three-level system. Now E2 being a metastable state, therefore tau 21 will be always greater than tau 32, and Wp is always positive. Therefore entire quantities on the RHS is greater than 0. That requires that represent basically the sufficient condition for population inversion. Now let us denote one quantity, ratio of tau 32 by tau 21 by beta. Then equation 12 is written as Wp times tau 21 greater than 1 divided by 1 minus beta. So that's the condition for population inversion. So minimum pumping rate required to achieve population inversion is called threshold condition, which is nothing but equating the equation 12 or equation 13. So that can be written, if you equate it to equation 12, the threshold population inversion condition is written as Wp threshold equals 1 by tau 21 minus tau 32. Now, in order to understand that, let us plot a graph of delta n versus Wp tau 1. Now, the curve starts from very negative value to and goes up to positive value, showing this, and reaches a saturation value around n0 by 2. So this also defines the threshold radiation required, which is much above the value of 0. Wp should be much higher. So that's actually this after studying this, one can understand that lasing is indeed possible in three-level system. Conclusions. Initially N1 is always greater than 1 and nearly N0 by 2 number of atoms must be transferred to N2 to achieve population inversion. Okay, so that's actually basic requirement to achieve population inversion and also requirement to achieve lasing in the system. So this tells actually a three-level system for this reason is not an energy efficient system. This information can also be obtained when we study four-level system, which we are going to study in the next class. A ruby laser is an example for a three-level system which is found to be very low efficient laser. So practically whatever three-level laser system so far discovered, they are all found to be having low efficiency. So that ends the lecture. Thank you for your